part one of circles. Prior to doing that, there's some vocab we kind of need to discuss. First one we know about circles is the radius it's actually two things. The radius is the distance from the center of a circle to any point on the circle, and it is also the actual segment that connects the center to any point. The diameter is a segment that has both its endpoints on the circle that goes through the center. So a chord, like a diameter, has its endpoints on the circle. It may or may not go through the center. If it does, we call it the diameter. If it doesn't, it's just called a chord. If a line crosses through a circle twice, that's called a secant, versus a tangent only hits it once. So we have the center of the circle right here. Any angle that goes through the center has its vertex is called a central angle. Circles are congruent, so if we talk about some of our, our similarity stuff, but they're congruent. They're the exact same if they have the same radii. So they can be in a different location, but same radius. That's the only thing you really need for a circle is the radius. And if you're going to talk about where it's located, you would also need to know its center. All circles are actually similar to each other. You can use a size change to get the exact same radius. I'm talking about arcs and chords when you have those congruent circles. If there are two arcs that have the same measure, so if on a circle there are two spots, now this one we really don't have any, but just imagine we have this arc right here, and then somewhere else there's another arc, then they have the same measure. If I connect this point to this point, however long that is would be the same somewhere else that has that same arc measure. If you flip that around, if the chords are the same, then their arcs would have to be the same. Okay, the next theorem is called the isosceles triangle coincidence theorem. If we have an isosceles triangle, you see this picture right here, there's a lot of stuff going on, but the bisector of the vertex angle right here, vertex angle. So if you don't remember from isosceles triangles, we have the base angles, which are those congruent angles, the sides that are the same. If we bisect this vertex angle up here, a couple things happen. We are bisecting it, so those two angles are the same, but it actually is going to intersect the opposite side at 90 degrees, and it will also split it in half. The main theorem that we're focusing on has a couple different parts. First one, if we have a chord and it is being cut through the center, this theorem tells us that the chord gets bisected. Second part, again, if we have a chord and this time we know that it's been split in half, it also is going to split this angle right here. Kind of going off of that one, if that angle is split, if that's the given information that we know, then it's also bisecting the chord. Those go hand in hand. But we also know that it's crossing at 90 degrees. And the last one, if you are bisecting a chord at 90 degrees, so perpendicular bisector, it will go through the center. We can find chord length, so the actual length of the chord, we can use some of our trig stuff. If we have our special right triangles, 30, 60, 90, 45, 45, 90, those are going to be useful. Kind of nice to not have to punch something into a calculator when you have those special cases. Let's look at our first example. So it's asking us, how long is this chord right here if the arc is 120 degrees? Now they could tell us the arc, they could also tell us the central angle. Those are actually the same. If you think why, there's 360 degrees in a circle, and there's 360 degrees around a point. But let's say this is the given. We have this angle up here, and we have this measurement right here. The process that we use, and after you do it a couple times, you maybe don't have to draw the picture and go off of that, but we are going to split this triangle in half at 90 degrees, so it looks like those pictures from before. That now gives us a right triangle. That actually gives us a 60-degree angle right there. So that's our 30, 60, 90 right triangle. Given the hypotenuse, we can find the long leg. First step is finding the short leg. Remember, those are related by either doubling or cutting in half, depending on which direction you're going. Short leg times radical 3 to get the long leg, but there are 2 of those. We will then add those 2 together. The final answer without a calculator is 7 radical 3. Some applications you would actually want to type that in and have it in as a decimal. Okay, second example, let's say our chord now is 44 degrees. The diameter is 14. Remember, diameter is double the radius. You know the radius is 7. That's the first thing I'm going to put down on there. But now we're going to repeat that same process. We're going to split the triangle in half at 90 degrees. We know this angle down here is going to be this one split in half, so it's 22 degrees. It's not a 30, it's not a 60, it's not 45. So we're going to use our trig. We're trying to find this entire chord length, but we're just going to focus on half of it first. So that is our opposite side that we're trying to identify. I'm going to call it x. This is our hypotenuse. So we got opposite, hypotenuse. It's going to be sine. Sine of our angle, opposite over hypotenuse. We're going to solve that with multiplication. If we double it, that's going to give us our final answer, 5 2/10. So this one, again, it's approximate, it's rounded, that's okay. All right, our last example, same picture from before, same information, but a different question. It's asking us for the length of the arc, not the length of the chord. We know our answer from before, so we know it's going to be a little bit more because it's kind of bowed out. We know circumference is either 2 pi r or pi times diameter. We don't want the entire distance around the circle. We only want 44 degrees of that. So if we know 44 degrees, the whole thing's 360. This fraction right here, we are then going to multiply it by pi and the diameter. We punch all that stuff in, and it gives us an answer. If I leave the pi in there, sometimes we like that. Here's the exact answer with a repeating decimal, or the one that makes a little bit more sense. And you can see, we mentioned the previous answer was 5 2/10, and this one's 5 38 hundredths. It is just a little bit longer as it's curved out.